Okay, so now we're going to take a look at a variety of different illustrations of restraints that might be in a piping system so we can review how this could be modeled in Caesar 2. Here's a piece of pipe that's supported off a short angle iron that is connected to some foundation. Well, I would put the restraint at the pipe center line, and this restraint is in the Y direction. So I would specify at whatever node number that node is on the piping system, I would say a Y restraint, both plus and minus. I would also put in an X restraint because that U-bolt prevents it from moving laterally as well. Now, that would be my model in Caesar 2. But let's say I look at my results and I'm coming off of some riser from up above and I get a lot of negative Y load on this angle iron. Or let's say the angle is very long, and if I have a larger load on that, I might be able to displace it. Right now the stiffness is rigid because it's blank. Well, while this model here would be adequate for light load, if the load, let's say in the Y direction, gets large, I would want to either come back in and put in stiffness or actually model this angle. But then you get in the problem with modeling stiffness of true steel out there in the field. The structural engineers normally want to see what the load is that they have to carry, and now we are trying to change the carried load by the deflection of the steel, which is something that structure side probably wouldn't want us to do. So this would be the adequate model in most cases, but again, in reviewing the results, if I see a large number, then I might start to question the stiffness used here. We have some people that say, well, hold it, if that U-bolt is really tight on the pipe, it may not be able to twist. Well, I think that's getting a little too complicated in our model. So I'd say just a Y restraint, double acting Y, double acting X restraint. Here's another common support. It's a base support. Now, here's the node number in our piping system, and that might be the point where you wish to supply the restraint. But we might actually want to put it to true support point. But here we have a plus Y support at that node on the pipe. Well, in fact, if I have friction, then I should put my restraint down here because this is where the friction will act and it could cause some overturning bending moment on the pipe. So if I'm going to throw in friction, now what value shall I use? Well, here I'm showing 0.15. Let's say it's a slide plate specially made to provide this coefficient of friction. Most times when it's steel on steel, people are using 0.3. Well, 0.3 is the textbook value for steel on steel friction coefficient. Here in the Texas Gulf Coast, a lot of this outdoor piping is subject to lots of corrosion, and it's hard to count on that stiffness or that coefficient of friction being present. So if I'm close to equipment, rotating equipment, then I'm going to want to get a better number here, more accurate number. If I'm, let's say, out in the middle of a yard piping, then I'm not too worried about the number here because it's not going to affect the piping system to any great amount. Here's your typical shoe support. Now, a lot of people say, well, this is a guide. Well, in Caesar 2, it won't be only a guide. It is a guide and a plus Y. These are two separate restraints. So I'll have the plus Y restraint because the pipe can't move down. It can only move in the positive Y. And I will put a guide on the pipe as well. And I can define that guide either with my global term X or the local term guide. This will be a restraint that is perpendicular to the pipe and in the horizontal plane. As noted other times in these presentations, if I have a piece of pipe that is going in the vertical direction and I have a guide on that, the program will automatically put an X and a Z restraint on it because there's an infinite number of perpendiculars in the horizontal plane. Now, let's go back to this plus Y restraint. Let's say you look at the results for some load case and you actually see the pipe move up in the output. And that's legitimate because that's the way we define it here. But here you are defining a restraint, building a restraint out in the field to carry dead load, and it's actually lifting off of that support. If the pipe lifts off of the surface, the program would report that, and that would be a good analysis, but it probably is not a good design, because if the pipe lifts off of a shoe like this, you probably would have to find better locations for this support to carry load in every load case. Now here's a support. The pipe is resting on some foundation. There's some big space on either side and a bit of gap up above. You can make this quite complicated or keep it rather simple. As you leave it simple, then it's up to you to review the output to make sure there are no mistakes or improperly modeled conditions here. So here I will say I've got a plus Y restraint. Now I could say Y or plus Y. We have this little gap here. My guess is that this pipe is always supposed to be resting on the surface, and I should not expect it to lift up. And if I show it as a Y restraint, I should always see a negative Y load in all the restraint reports. If I model it as a plus Y restraint, I would monitor the displacements, or I'd make sure that if there's any zero load on these restraints, that it is trying to lift off. Then I would have to worry about that gap. I might also worry about this gap on either side. I'm going to assume that this is made large enough so the pipe does not come in contact with those limits. It's basically to protect the pipe, not to limit the pipe in its motion. If I wish to model that, I could model that as an X restraint or a guide in the X direction, and I'd specify the gap. If I don't want to put this in the model, what I will do is in the output, I'll check the horizontal deflection in every load case to make sure it is less than this amount. Then I know it doesn't come into play. Here's the support. We are resting our pipe on steel, and we're also limiting the axial growth or any axial change in position here. This will be a plus Y restraint, and will also be a line stop or limit stop in Caesar 2. I could either say X, or the word limit would be a restraint in the same direction as the pipe on which it is provided. The stiffnesses are rigid, very stiff in there. Now, the other item that might come into play here is a rotation about Z-axis. If this pipe wants to rock up or down, we could seize up this support and it can't rotate. But then as soon as it starts to rotate, it could turn into an anchor. So this might not be the best support if you want to get any deflection out of it. Are there gaps? Well, certainly there has to be gaps if you don't want it to seize up, but I'm not going to spend the time to model it. Again, if I get very large loads on these restraints in my output processor, then I might want to come back and take a closer look at this. Here's a roller support. This is mainly just a plus Y restraint. Nothing more than that. The other issue, though, is some would say, well, look, it's got to come up out of that. If it wants to move laterally, it has to go up before it comes out. Well, if I'm using a roller support like this, I might have upstream of this point a nozzle to a piece of equipment, and on the downstream side I have some guide. But this support by itself does not guide the pipe. It will be the restraints around it or the conditions around it that would guide it. Here's your typical anchor. I would put an anchor, but right now I've got it at the center line of the pipe. It depends on how stiff this section is here. If the stanchion is very long or small in diameter, then I might want to get that stiffness in my analysis as well. So I'll run an element from the center line of the pipe down to the true support point and put the anchor down here. So it'd be an anchor either at the center line or at the true anchor point. And again, if I put it up here and I get low loads, it probably doesn't matter if I put it up there or down below. But if my loads are high, then it's more important. Another common support, a dummy leg off of an elbow, either with steel like we see here or just pipe. Here we have a restraint that's defined right here, right on the circumference of this elbow, center line of the elbow. Again, if I'm out in the middle of a pipe rack and I'm just dropping down one level, that model right there is just fine. But let's say over here at this end I have a piece of equipment where I'm concerned about the load in that equipment. Well, now I'm going to be very concerned about this support point. I might actually want to slide it over here and actually model this steel, either with steel directly in Caesar 2 or by an equivalent pipe size, to get this moment arm in here, to get a better calculation what's going on over here. Another issue is that I've got this weldment on the elbow. This elbow is not as flexible as a standard elbow. So what you might do is maybe call out an elbow with flanges on it to stiffen it up. So as you get closer to equipment or sensitive areas, then you have to develop a more detailed model. But right now, we're just going to put a plus Y restraint out here and use the coefficient of friction in this model as well. That's up to you. Your shop might not use friction, but if you do, that's how you apply friction at that point as well. Here's another dummy leg, vertical leg off of an elbow, similar to the previous one, but here we have an issue where we could call it an anchor right there, or bring it down here to the actual anchor point. Again, putting it down here would allow me to involve the flexibility of this cantilever. If it's hot and this is insulated as well, this is going to grow vertically as well. So I can put the anchor down here. That's a true anchor. If I put it up here, then I might have to put in my own deflection setup there rather than an anchor. So these are the kind of things that come into play. Again, too, I might worry about the elbow stiffness. Since I'm welding on the elbow, it can't flex as it normally would. That's probably a very detailed adjustment here, but you might be able to get a better model if you account for that higher stiffness of the elbow. Here's a rod model. Now, look at this. You might say, well, the pipe can't move in the X direction, plus or minus. If I say it can't move in the X direction, I'm defining a plane of free motion, this vertical ZY plane. We now know, though, that this has got some arc associated with it. If it wants to move up, it has to move also in the positive X direction. If it moves down, it also moves in the positive X direction. So what this link here, this rod does, is doesn't give us a plane of free motion. It gives us a sphere of free motion. And calling out an X restraint by itself will give me the plane. How do I get a sphere of free motion? Well, I put in the rod model. So the one important thing about using rods in Caesar 2 is they must be signed. If you don't put a sign on it, the program assumes it's in the positive direction. The sign indicates the pivot point. If I say plus X rod, this is the pivot point. If I say minus X rod, the pivot point will be over here. The vector would go negative, so it would sweep this way if I say negative X. So I do want to say plus X rod, and then my modifiers change. Here it says the length of the rod is R. That will give us a sphere of free motion. And I could also specify my stiffness. I'm leaving it rigid. And if it is a spring can of some sort, I could put on an initial load on that spring can. So this is a little more complicated model. One other point here as far as good design, I know in the B31.1 code, they used to limit rotation on rods, usually vertical rods, by no more than 4 degrees. So if we actually do get a lot of motion here, that's going to break that rule of limiting the rotation. And I guess the main reason for that is if it's stable in the installed case, it should be stable in all of the load cases. And we don't want to see this coupling of the Y direction with the X direction in the analysis or in the design of the system. Okay, and one more for this segment. Here's a shoe, but now it's clipped down. We see it wrap around. This is similar to the shoe we had earlier, but the other one was a plus Y restraint. This one is a double-acting Y restraint. And we also have a guide. All right, so we have a guide or an X restraint along with the Y restraint. I might also concern myself with friction in here. Probably not in the horizontal direction, but certainly in the vertical direction. The dead weight normal load would cause some holdback on the load. Okay, in our next session, we'll continue on with some more of these examples.